What if our sun became a black dwarf? Imagine, for a moment, a time so distant that the great civilizations of humanity have faded into the mists of history, the continents themselves have shifted and merged beyond recognition, and even the stars in our sky are different than the ones we know today. It is in this far, far future, trillions of years ahead, when our sun, Sol, has finally completed all the phases of its stellar life and has become what astronomers call a black dwarf. But what does this truly mean for the sun, for Earth, and for the future of the universe itself? Let's embark on a journey through the deep tapestry of time and ask, what if our sun became a black dwarf? To understand this distant scenario, begin by considering the life cycle our sun is currently following and the stellar evolution that awaits it. The sun, as we know it today, is a main sequence star, one that spends most of its life converting hydrogen to helium in its core through nuclear fusion. This phase of stable burning lasts for about 10 billion years, and right now, the sun is about 4.6 billion years old. That means it's nearly halfway through this period, shining in the familiar, steady way that has given Earth the energy necessary for life as we know it. But stars, like all things, have life cycles. In perhaps 5 billion years hence, the sun will exhaust the hydrogen at its core. With fusion no longer able to hold up the immense mass of the sun's upper layers, gravity will take its turn, compressing the core and heating it once again. This shift triggers the transformation from a main sequence star to a red giant. The sun will expand, growing so enormous that it will likely engulf Mercury and Venus, and possibly even Earth, though by then our planet's oceans will have long since boiled away, and its surface rendered uninhabitable. The red giant phase is a spectacular but temporary chapter. During this period, the sun's outer layers will be ejected into space, drifting away to form a colorful, glowing shell of gas, known as a planetary nebula, the final fleeting fireworks display of a dying star. What remains of the sun is the hot, dense core now exposed, a white dwarf, about as massive as the sun today, yet compressed into a body no larger than the Earth. As a white dwarf, the sun will have ceased nuclear fusion. It will still glow, but only from residual heat, a cosmic ember cooling quietly in the darkening universe. For eons, far longer than the sun's entire previous lifetime combined, this remnant will linger, gradually radiating away its last reserves of energy. Yet even this isn't the end of the story. Given enough time, the white dwarf's radiant heat will dissipate fully. It will fade from white to red to black, no longer emitting visible light at all. This ultimate fate, a cold, blackened sphere, is what we call a black dwarf. But here's the twist. The process of cooling from a white dwarf to a black dwarf takes longer than the age of the universe itself. Our universe is about 13.8 billion years old, and even the oldest white dwarfs are still glowing hot. Models suggest it could take a quadrillion years, a million billion years, for a white dwarf to become cool enough to qualify as a true black dwarf, so cold and dark that it no longer shines. No black dwarfs are thought to exist yet. But let's posit the thought experiment. What if our sun did become a black dwarf? What would this truly mean, not just for Earth, but for the cosmic tapestry our sun has belonged to for so long? Picture the sun, now a black dwarf. No longer a source of heat or light, just a cold, dense relic hanging in space. To comprehend the magnitude of this transformation, let's explore the cascade of changes that would ripple outwards. First, imagine the solar system itself. Without the nuclear furnace of the sun to warm it, the family of planets would be cold and silent. For Earth, this would have been the case already for unfathomably long ages, since humanity's time on the planet would have ended long before the sun reached even the white dwarf stage. If any remnant of Earth still orbits the sun at this distant epoch, it is utterly frozen, a world of extreme eternal night. The energy output of a black dwarf is virtually zero. No new light, no new heat, just the faintest whispers of remaining thermal energy, so slight as to be undetectable from any practical distance. Planets, moons, and asteroids find themselves orbiting a quasi-invisible mass, a gravitational anchor with no radiance. What would happen to the orbits of the planets themselves? During the transition to the white dwarf stage, the Sun will have lost about half of its mass, shed in solar winds and planetary nebula. This mass loss will cause the orbits of the remaining planets to expand. If the Earth remains, it could be farther out, circling slowly around this now invisible object. With less mass at the center, the gravitational grip is weaker, but stable orbits could persist for a time, unless perturbed by other cosmic events. Over astronomical timescales, the solar system becomes a haunted echo of its former vibrancy. Occasionally, a wandering star might drift close, unsettling the delicate orbits and flinging planets into interstellar darkness. Even the planets themselves, slumbering in the dark, would be dramatically transformed. Any atmosphere would have frozen out long ago. Any water planet might now be solid ice, denser than rock under crushing pressure. Without the Sun's influence, cosmic debris and the leftover bits of the solar system, asteroids, comets, even distant Kuiper Belt objects, face a cold, quiet eternity. Some may ultimately fall into the abandoned, lightless Sun, spiraling down across deep time. Others may be ejected into the interstellar void. Beyond the literal darkness, perhaps the most poignant effect is the symbolic end of an era. For billions of years, the Sun has powered life, driven weather and climate, and shaped everything in our solar system. As a black dwarf, it is a remnant, a tombstone marking the story of a once luminous star. The processes that forged the elements necessary for life are finished. But what exactly is a black dwarf? It is, in essence, the endpoint of a journey dictated by physics and time. After the ejection of its outer layers, the former core of the Sun, the white dwarf, is left as a degenerate object. In this state, atoms are packed under immense gravity, electrons providing the pressure to keep it from collapsing further. At first, this remnant glows with heat left over from the core and from the violent events that created it. But there's no longer any source of new energy. With each passing era, the white dwarf radiates away its heat, cooling so slowly that, even after trillions of years, it remains hot, long after any ordinary matter would have cooled to the cosmic background. As the white dwarf cools, it eventually reaches the same temperature as the universe's background microwave radiation. Only then does it truly become a black dwarf, a sphere of carbon and oxygen, crushed to unimaginable density, so cold as to be utterly inert. It no longer shines, it no longer glows, it no longer carries the memory of the star it once was, except for its mass and its composition, a silent legacy to its primordial origin. What about the universe around our extinct Sun? The scenario of black dwarfs emerges in a universe in which all star formation has ceased, where the last flickering red dwarfs have sputtered out, where galaxies are shrouded in darkness and matter flees into the infinity of intergalactic space. These black dwarfs are, in a sense, the corpses of ordinary matter, marking the epoch known as the degenerate era, a time in cosmic history where the active, visible processes of the present age have faded to a dark aftermath. In this far future, what remains are the cinders, black dwarfs by the trillion, neutron stars, and black holes, all drifting in eternal night. Occasionally, over mind-bendingly long timescales, quantum tunneling or gravitational disturbances lead to rare events. A black dwarf might experience a quantum supernova, or colliding with a black hole or another stellar remnant. But by and large, the universe will be a place of silence and stasis. But could anything persist, any structure, any civilization, in the aftermath of our Sun's extinguishing? The reality is, by the time Sol becomes a black dwarf, the Earth would have long since ceased to be habitable. The transition to the red giant phase destroys the biosphere, and the cooling white dwarf provides no energy to sustain life. Any intelligent beings evolved from our lineage would have needed to leave Earth far earlier, or to find new methods of obtaining energy. Is there any physics that could power life or culture in a system orbiting a black dwarf? Practically no. Without starlight, without warmth, the only energy sources for life would be the faintest of tidal effects, or perhaps the last radioactive decay within planetary interiors. If life persists at all in the degenerate era, it must find ways to exploit physics at a scale and creativity almost unimaginable to us. From a human perspective, the journey of a star from shining main sequence to cold black dwarf is scarcely comprehensible in its duration, its slowness, and its enormity. To compress billions upon trillions of years to a simple narrative is to flatten centuries of history into a single sentence. What about the fate of information itself? Will the memory of the sun ever be truly lost? In the heatless, lightless depths of the black dwarf era, information, whether in the form of civilizations, messages, artifacts, or even records etched in the orbiting remnants of destroyed planets, faces obliteration by entropy, accidental destruction, or eternal isolation. Yet in another sense, the final black dwarf remains a kind of record, a time capsule of the sun's history. Within its mass and its makeup are the elements the sun forged over billions of years, the traces of the nuclear reactions that powered it, and the evidence of the processes that shaped its life and death. If any intelligent observers exist in this era, machines perhaps, or cosmic travelers, they might decipher the story of a star and its system from the black dwarf's quiet ruins. Let's briefly reimagine the full timeline of the sun's ultimate transformation, from our present epoch to the age of the black dwarf. First, for the next few billion years, the sun continues more or less as it is, a main sequence G-type star. Life on Earth continues, or perhaps ends, as our technologies and societies change. After hydrogen runs out in the core, the sun expands into a red giant, engulfing, burning, and remaking the inner solar system. Its outer layers are flung into space, shaping a planetary nebula. The core, now a white dwarf, remains, initially hot and bright but quickly cooling as it radiates away the last of its energy. For trillions upon trillions of years, the white dwarf cools, fading ever further as its heat is lost to the remorseless flow of entropy. At last, after quadrillions of years, far longer than stars have even existed, the sun completes its journey, settling into darkness as a black dwarf, more ancient than any memory. Older than any legend, a silent gravestone for a once brilliant star. What, in the end, does it mean for the universe that our sun will become a black dwarf? It is the final destination for many stars, but not all. More massive stars become neutron stars or black holes, far stranger and more violent endpoints. But for stars like our sun, ending as a black dwarf is a gentle decline, an eternal stillness after the drama and passion of a star's youth and middle age. It is, perhaps, the ultimate quiet. The silence after the music has long stopped. Some theorists, looking at the far future of the universe, have speculated that black dwarfs themselves might not be the end. Over timescales inconceivably vaster than anything we can imagine, our universe will continue to cool and expand until even the dust between the stars is separated by trillions of light years. Even black dwarfs, held together by electron degeneracy pressure, could eventually see their protons decay or be disrupted by quantum tunneling, so-called black dwarf supernovae, a hypothetical phenomenon occurring over timescales of 10 to 1100 years or more. Should this happen, the material that was once Sol would be scattered into ever thinner, more diffuse soup. Even atomic nuclei might not last forever. In some cosmological scenarios, all matter decays, leaving only the thinnest mist of photons, neutrinos, and perhaps incredibly faint gravitational waves as the final residue of the cosmos. Yet, in imagining the black dwarf that our sun becomes, one is reminded of the sheer scale of cosmic time, the fact that all we experience, all we know, even the histories of life and civilizations, are just a flickering instant in the life cycle of a star. Our sun, the familiar point of light in the sky, is not immortal, but it is one of the slowest and most enduring presences in our lives. How, then, does this influence our view of ourselves, our place in the cosmos, and the destiny of everything we build? There's a kind of humility in understanding that, however grand our ambitions, the universe operates on scales and times far beyond our lifetimes. The rise and fall of civilizations, the growth of cities, and the construction of monuments, these are all, in cosmic terms, ephemeral. But perhaps there's comfort as well in the knowledge that our sun's story, though finite, is a part of an even greater continuum. Long after we are gone, even after biological life on Earth has ended, the sun's material endures. A final cold relic of a star that once shone over oceans and forests, cities and deserts, poets and scientists and dreamers. To summarize, if our sun became a black dwarf, it would mark the endpoint of a protracted destiny. The warmth and light that nourished our world would have faded first into a red glowing ember, then a faint white dot against a much darker sky, and finally into invisibility. No more dawns or sunsets would bless Earth's skies, and all evidence of the sun's vital, burning heart would be compresses into a cold, silent cinder. It would still exist, exerting its ever-weaker gravitational hold, but stripped of all radiance. The universe, by this epoch, is unrecognizably different. Galaxies swirl in slow isolation. The fabric of space stretches ever outward, and the inventory of active, fusion-powered stars shrinks toward nothing. For tens and hundreds of trillions of years, white dwarfs continue to cool, their faint glows a soft echo in the deepening darkness until, at last, they are snuffed out as black dwarfs. At that point, our sun's legacy is twofold: in its material, the ash and carbon that once burned so brightly, and in the fleeting dance of planets and debris that remain bound to its unseen gravitational pull. Its influence is no longer found in radiance, but in memory, a stage completed in the vast theater of cosmic time. As we pull back from this far theoretical future, we might reflect on our own moment in time. Luminous, vibrant, yet finite. A glimmer in the twilight before the long, quiet night. The sun as a black dwarf is the ultimate memento mori, a reminder of impermanence, but also of endurance, as even in darkness, the story of a star persists, written in the silent archives of the universe. And so, what if our sun became a black dwarf? The solar system would fall to silence and cold, the last remnants crumbling ever slower about a dark, unseen anchor. The light that once made life possible would have gone dim, but the record of its existence, its atoms, its gravity, and the story it left behind, would echo still, on through the endless night that awaits us all.